And then Stacy, you can start sharing your screen and
All right.
are jumping in.
All right. Thank you very much. And
And feel free to start, Stacy, whenever you're ready, because participants are already in and can hear you.
all right. All right. Thank you very much. Hello and good morning. Happy Friday. Hope everyone is staying nice and cool. So my name is Stacy Anderson, and I am a math coordinator with Merced County Office of Education. I just first like to always start off with our vision at MCOE that every student is enthused about mathematics and sees the value and beauty of mathematics and is empowered by the opportunities that mathematics affords. This really resonates with me. Growing up, I was loved school. I always knew I would be a part of education. But I was told that I wasn't very good at math. And in fact, I was encouraged not to take any more math because it was hurting my GPA. So, you know, I wanted to be an architect, but grateful that I got steered into education because of the change that mathematics has played in my life. And then going back and realizing that all children can learn and understand mathematics in a way that makes sense to them. So, and why is my screen not moving? Okay, so we do have a hierarchy. So just thinking about Maslow's hierarchy of needs, we also have a hierarchy of needs when it comes to mathematics. And the very basis of this is this teacher content knowledge. And I think it's sometimes hard in early education because we all know that we can all do kindergarten math, we can all do first grade math, we can all do second grade math, but there's a difference between doing the mathematics and understanding the teaching of mathematics. And so that's something that we just really want to concentrate on, is thinking about all the components that goes into teaching of mathematics. And then with that hierarchy, we also have this early education hierarchy of needs. So just kind of thinking again about those material needs, including the teacher's understanding, and then the mindset and culture that we can all learn mathematics. And so I like to start off with the video. It's a kid snippet. You know, I want to say that, let's see. It would be nice to say that we haven't been here, but I tend to find this humorous because we have been here before.
Okay, here's your homework. First let me tell you the directions. What's 4 take away 5? 1, 2, 3, 4, 5, 6. Take away. What's 6 take 1? 1. No, you take away. So you take away 1 out of 6. How much does it equal? What's 10 minus 1? I don't know. 1, 2, 3, 4, 5, 6. 6, 7, 8, 9, 10. Nope. Take away 1. How much is it? 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6, 7, 8. and one more, and add one more. How many is equal? One, 2, 3, 4, 5, 6, 7, 8. One. It equals, it makes 9. See how you take away? You take away 1 and it equals 1. Mm-hmm. Do you get it now? Yes. Again. 1, 3. Yes. Good job.
So, oops, I was reading here. No, 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 no.
Wait, so the new camera's doing the same thing the old camera did? Yeah.
Okay.
Stop. Continue. Go hard.
All right, let me get the right thing up. Okay. Sorry about that. Okay. So hopefully you were able to see that. And what's interesting is that we can all feel the pain in that understanding of thinking that we've explained something thoroughly and then the kid's not understanding it, right? So I want you to go ahead and look at these numbers and take 8 away from any of the numbers that you would like. Think about what that would look like. So if you took it away from 20, you'd get 12, away from 10, from the 10, you'd get 2, or away from the 8, you would get a -3. And then just kind of thinking about, what if it was 35 minus 8?
Stacy, we don't see your screen.
So you're not seeing my screen. All right, thank you. Let me see why. Okay. Yes. Okay, desktop. Sharing screen, your screen is sharing. Are you seeing it now?
We can see it now.
All right, thank you. Okay, let's try this again. So if we go back, so 35 minus 8, 27, we know that. When we've done this, when I've done it with cubes and I give people cubes, kids and adults alike, they usually, like, so if you build your 38 or 35, excuse me, 90% of the time, yeah, I'm throwing that number out there. Most of the time, we'll just say, most of the time, people will take one of their 10s and just take 2 off of it. When I ask why, they'll say, well, because they know that 8 and 2 make 10. So they just take the 2 off, leave the 2 there, and move the 8. So kind of that idea that really most of us tend to take that 8 away from that 10, rather than the 5, which is, if we think about that standard algorithm, that's how we teach kids to do it, which just is not really a natural way that we would automatically do that unless we've been taught those steps. So then when we're talking about what is subtraction, what is number sense, and what is fluency, is this subtraction? 13 minus 8, take away that 10, bring it over, we will have 13 minus 8, right? But a lot of us do this just naturally because we think of subtraction as being these steps. Also then I look at this, I taught 5th grade for years and years, and this was always on my, for back to school math assessment. Of course, thank goodness it hasn't been on for since I think the last time I did that was 2012 or 13, somewhere in there. But I would always put that idea of that 100,000 minus the 99,998 or 999. And I thought I was assessing subtraction fluency. And I realized I was not. I was seeing if they could do the standard algorithm, this idea of subtracting across zeros. And, now I question, is that really fluency? Wouldn't we rather just have our students say, 99,998, 99,999, 100, 100,000, and that idea that it's just 2, rather than doing all that craziness across the zeros. So number sense, as students work with numbers, they gradually develop flexibility in thinking about numbers, which is a hallmark of number sense. Number sense develops as students understand the size of numbers. They develop multiple ways of thinking about and representing numbers, use numbers as reference, and develop accurate perceptions about the effects of operations of numbers. So just thinking about what actually is number sense, and then how do we develop that, have that grow in children. So we do know that this idea of basic fact fluency requires the presence of flexibility, appropriate strategy use, efficiency, develop fluency with numbers, is develop number sense, is to work with numbers in different ways and not to blindly memorize without this number sense, which is what we used to think that number sense was, this idea. Can you recall all of your facts within a second without really thinking about it? And is that really what number sense is all about, or is that memorization? So I think it's just kind of understanding, what do we appreciate in number sense and mathematics, and what is our goal? We know that some of these foundations, that we know what we have to understand. We need to know our audience as teachers. We need to know our kids, right? We need to know our standards. We need to know about problem types and questioning. We need to know the mathematical practices. We need to know engagement strategies, engagement activities, and we need to understand manipulatives, and that kids of all ages need manipulatives. I love the analogy, it is amazing how many classrooms we go in that there aren't manipulatives available for kids. And I know as a teacher, this idea, well, they're just going to play with them. Yeah, they are going to play with them. But the more they're out there for them to play with, the more they get used to, and they just become part of this math tool. I love the terminology, this idea that our first graders, our second graders, our third graders, they need manipulatives. And if we withhold manipulatives from them, it's just like a doctor and malpractice. This idea that you need a medication and you're not going to get it for, let's just say, for type 2 diabetes, well, you can control that with weight and or with diet and exercise, right? But it's the same idea that we need to give our kids the tools that they need in order to learn. And we know that they need this hands-on, human beings need this hands-on learning. So we want to make sure that they have those things that they need. So building strategy with number sense, we know that contextual problems is, I would say, by far the most important things that we can do. Every time we're talking about maybe taking something away, right? We should be doing it in a word problem, in a number problem, in story problems. It's not this idea that we have to understand numbers first, and then we can give them word problems, right? It's this idea that numbers make sense in real life. They're not just these magical things that we do stuff with, but you know, we all can understand that if we have 3 apples and I give 1 apple to my sister, how many apples do I have left? I have 2 apples left, you know. Every human being can understand that type of thing if it makes sense to us. So we really have to think about those contextual problems. We're also then trying to look at patterns and relationships, problem strings, number strings, fact families with that inverse operation, you know, counting collections, asking questions, you know, all different ways of building number sense within our kids, within our students. We know that we need, in order to learn, we have to have this idea of being able to problem solve, right? It's just kind of like that idea of that. How are we going to teach kids to be problem solvers if we don't give them those problems to solve? So again, I'm going to encourage my students at very young ages, in preschool, in TK, in first grade, and you know, that those ideas that, hey, you know, you've got 5 frogs sitting on a log and 2 frogs jump away. How many frogs do I have left sitting on that log? Oh, okay. So yeah, so my math story here, we have 5 green frogs sitting on a lily pad in the pond, and 2 of the frogs jump into the pond. How many frogs are still sitting on that lily pad? And so we might want to say, you know, why do we need to understand, or why do we need to have it in contextual understanding? And this video, this is of 8th graders solving a word problem. And I'm sure many of you have seen this, but I just think it's really important for us to look and see, because technically, well, I'm going to let you watch and see it, and then we'll talk about it.
There are 125 sheep and 5 dogs in a flock. How old is the shepherd?
What? There are 125 sheep and 5 dogs in the flock. How old is a shepherd? I don't know how to solve this
Why is that?
because it doesn't talk about anything about the shepherd. Like, doesn't say how old, like how long he's had them or anything. So like, it doesn't give me any hints about anything. Yeah.
Okay. Thank you very much. There are 125 sheep and 5 dogs in a flock. How old is the shepherd?
$120 old.
How do you know it's 120? Can you please write down here? And how do you know that the shepherd is 120 years old?
Yeah, let's subtract 125 minus the 5 dogs in a flock.
Okay, thank you very much. Thank you. Can you tell me, how did he know to divide?
Because it doesn't say the difference, or it doesn't say the sum or the project or something.
I see. Okay, thank you very much.
Those mathematical practices are key as we're teaching students. Yeah. Oops. Okay. All right. So any thoughts? You don't mind putting some things in the chat? Some thoughts you have about contextual understanding and making sense of problems. And whoops. Yeah, definitely. Yeah, Janet had said that, you know, kids, they think they just have to do something with numbers, right? And it's this idea that let's just take these numbers and do something with them. You know, this idea of building number sense in kids, of letting them make sense of numbers in the world around them. I just think it's so important. You know, I was in a 6th grade classroom not too long ago. It's been a little bit, but you know, we just were throwing out some problems with the kids, and the teacher threw out, she wrote on the board 2 + 1/2, you know, and thinking this was kind of going to be the quick and easy thing to move up. And the kids the 6th graders really struggled with that idea of this 2 and 1/2, because they're trying to turn, you know, they're trying to find common denominators. They're putting a 1 underneath the 2. They think they have to do all this stuff to numbers rather than just making sense that, oh, if I walk 2 blocks and I walk a half more block, I've walked 2.5 blocks. And then if I take away, you know, if I have 2.5 cookies and I eat 1/2 of the cookies, how many cookies do I have left? You know, I have 2 cookies left. This idea of just making sense out of it, and that we really want to work on with our kids. So in TK, you know, these are some of the important, I'm not going to read over all of those, but just some of the important things as I was going through the California oh my goodness, the foundations. I've been reading the preschool foundations and then the frameworks, the California frameworks. So these were just some of the heavy hitters for each of the grade levels. Not saying that this is the only things, but these are just some of the heavy hitters that we want to really concentrate on in these grade levels. So our problem types, so math problem types. My first, I don't know how long, ever long I was teaching, I guess my first 13 years that I was teaching, and I mainly taught 5th and 6th grade is what I mainly taught. I thought that I guess I thought about mathematics as this hierarchy of things. Okay, first we need to learn how to do like addition, and then subtraction is harder than addition, but then multiplication, that's kind of hard, you know, and then division is obviously the hardest, you know, hardest of the 4 operations to do. I'm kind of in, you know, in our head as I'm thinking of this hierarchy, without knowing about problem types and thinking about that, you know what, we traditionally teach subtraction, like when we're doing these part whole problems or the comparison problems, we generally teach kids that this is subtraction. But the idea, you know, that Mrs. Jones has 8 students and 5 chairs, you know, how many more chairs does she need? Well, that kind of leads more to adding up rather than taking away from. So these ideas of, do we understand problem types, and that's really what causes the math to be more difficult or less difficult. So this idea, of joining, the idea of a join, result, unknown. Mrs. Smith has 6 cookies, and she gets 3 more cookies, and how many cookies does she have? Those types of things that can be directly modeled, those are very easy for children to solve. So anytime a child can act something out, when we have this direct modeling that can happen, we know that's going to be the easiest type of problem. But then when we're moving into these ideas of comparing problems, those are much more difficult. So that idea, for instance, 8 kids and 5 chairs, we can leave it at that. So, how many, but by asking questions of the kids, well, how many more chairs do we need, can help those kids be problem solving and thinking about that. So sometimes we can make the problems easier by helping them through asking questions of them. And so I just think it's really important, especially in earlier education, that we know our problem types when we're dealing with our stories. We know those things that the kids are gonna struggle with. And yeah, I know we don't generally get into the multiplying and dividing until 3rd grade. But in order to build number sense, I would highly recommend, and most of our math experts would recommend this idea of playing around with that idea of multiplying, because we know that our number system, our base 10 system, is based off of multiplication and division, that times 10 and divided by 10. So just that idea that, can I have 5 buckets, and can I have 2 frogs in each bucket, and how many frogs do I have? That our little ones can solve that also when we're doing it contextually, where it makes sense to them. So a join, change, unknown. Mr. Lee's class has students. When Mr. Lee counted the chairs in his class, he only had chairs. So this idea that I would want to talk to the kids, we're going to read this, together, or I'm going to read it to them, because that's something we get a lot. It's like, oh, well, my kids can't read, so they can't do word problems. Well, no, we can read it to them, right? We can talk about it with them. That's how we make sense of the world around us, right? Through talking about it. So if Mr. Lee's class has 28 students, when Mr. Lee counted the chairs in his class, he only had 17 chairs. And then I want the kids to think of what question do you think we're going to ask? What do you think the question's going to be? Getting kids to understand how to ask a question is huge, and we don't generally do that. In schools, we ask them questions, but we forget to allow them to ask the questions. What do you think that question is going to be? How many more chairs does Mr. Lee need so that each of his students has a chair? And that idea, kids can act this out. Kids can understand. Students, we've got 28 students and 17 chairs. So how many more chairs do we need? Again, traditionally, this would have been taught as a subtraction problem. 28 minus 17, right, is going to get us how many more chairs we need, because we have more students than chairs. But thinking about it this way, how many more chairs do we need so that each kid has a chair? Are we going to say, okay, 17, 1 more is 18, and then 10 more, would be 28, so we need 11 more chairs. And then how can we model that as teachers? How can we model that thinking? What did we do? Personally, I would use a number line, that idea of this open number line, that 17 plus 1 more makes the 18, plus the 10 more makes that 28. So that idea of jumping, in chunks. And some kids might say 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and 28, and counting it up on their fingers, And so can we do that together? And then how can I show as a class, what did we do? Maybe we think about it maybe we do then think about it as subtraction, this idea that, okay, 28 minus 1 is 27, minus 10 is 17. So there we have our 11 again. But tying that in together, we want our kids to understand this inverse operation with addition and subtraction so that they can fluently go back and forth between that. So the math practices, I've linked them here. So just this idea of asking questions, I really like this handout about the math practices. So number 1, make sense of problems and persevere in solving them. And then there is a list of questions that we can ask our kids that will help, that will help us. So much in education, I'm doing it right now. It's this idea of talking to people or talking at people, right? But we do know that in order to get our kids to think, we need to do a lot less talking and letting them do a lot more of the solving. And so, how can we do that with our students? And we know that one of those reasons is about asking them questions. So, what do you notice? What do you see? And those questions are huge. Number 2, reason abstractly and quantitatively, making sense of quantities and their relationships. So what do the numbers used in this problem represent? Which again is why it is so important to go back to contextual understanding, that if it's just this number, right? What do you mean? What does this number mean? But if we are talking about the frogs in the pond, we had 5 frogs sitting on lily pads in the pond and 2 of them jumped away. So what does this 5 mean? 5 what? Oh, 5 frogs. And 2 what? Oh, 2 frogs jumped away. Always going back to that problem so that we can make sense of what those numbers stand for, what those numbers mean. Construct viable arguments and critique the reasoning of others. Again, what mathematical evidence would you use to support your solution? So in other words, how did you know that? How did you see that? Do you agree? Do you disagree? Trying to decide, does that strategy work? Does it always work? Does it only sometimes work? But having our kids be able to construct those arguments and learn to agree and disagree with others is huge. So model with mathematics. What number model could you use to construct to represent the problem? What are some ways to represent the quantities? What can you do? Can you show me with the cubes? Can you show me? How can you show me what you're thinking about in your head? If there's the 5 lily pads or the 5 frogs on the lily pads, what can you use to represent that? Can you draw a picture of that? Again, can you use cubes? Using appropriate tools strategically. So we know we want our students to be able to understand how to visualize and represent their ideas, what's going on in their head. And what tools do they need to do that? Do they need cubes? Do they need paper and pencil? Do they just need to be able to explain, what they're doing? Are they using their fingers? Can we then tie that to a number line? Attend to precision. Again, going back and asking, about those mathematical terms. Is that solution reasonable? This idea of estimating, I love, I was just reading Joe Bowler's new book of Math-ish, this idea that so much of mathematics, so much of real world mathematics is this idea of estimation. And is that close? Is that even in the ballpark? So continually estimating, okay, so if we do have, if we have 8 frogs and some of them jump in the pond, are we going to have more than 8 or less than 8, and just having those conversations with our students. So it's not just about following these steps and coming up with an answer, which, if you have spent any time in, in elementary education with a worksheet, our kids, they will have something like, 100, I don't know, 102, minus 25, and we end up with 126 or something, and it's this idea, because all they're doing is thinking about following steps. And they looked at the sign and forgot which step they were supposed to follow. They added rather than subtracted, right? But this idea that, well, if we have 125 cookies, and 26 cookies are taken or sold or eaten, how many cookies do we have left? Are we going to have more than the amount of cookies that we started out with, or are we going to have less? And having those conversations with our students about that is huge into helping them to build number sense. Again, look for and make use of structures. And I'll let you look at some of these questions about that. We want our kids looking for patterns and relationships all the time. If you've ever done any choral counting, I highly recommend it. I did not realize all of the patterns that were out there. So for instance, we might count by fives, but we're going to start with 3. And so then we have 3, and then we have 8, and then we have 13, and then we have 18, and then we have 23, and then we have 28. And I was doing that for the first time, about 2 years ago, I want to say, and it was like, oh my gosh, I never realized that. Does that always work? And here I'm doing, counting by 5s, but I'm starting with 2s, or I'm counting by 5s and I'm starting with 7s. Wow, is that pattern always there? Very interesting, though, to see that we know that our number system, we know that all of mathematics, it's all about patterns and relationships. And trying to look at that big picture, what's the pattern? What pattern is going on there? What's happening there? Why does that work? Does that always work? And getting our kids interested, getting ourselves interested in that and seeing, oh my goodness, wow, that's pretty cool, right? So I think that's one of the things that I absolutely love about mathematics, is that I can still be amazed at times. It's like, something so simple would have never, just didn't think about that, Anyway, so I encourage us to play with patterns and relationships, look for structures in mathematics. So mathematical practice number 8, look for and express regularity and repeated reasoning. Again, will the same strategy work in other situations? So yeah, I was continually, like I said, when I first did the choral counting by 5, starting with 3, okay, is that always true? And needing to play with that, which kind of interesting as we watch our students play with different ideas and questionings. That is exciting. And also have attached, this is a bunch of different CGI math stories or tasks when we're talking about, and there's a mixture of different types, but just this idea, Steve has 14 boxes of colored pencils to share with his class. There are 6 pencils in each box. It's just listing a lot of different problems, and it's named the different problem types, going from some pretty basic to a little more sophisticated, again, with some pretty basic numbers. So this idea of 14 horses are playing in the pasture and 7 horses go to the barn to drink some water. How many horses were still playing in the pasture? And if I put it on slideshow, it starts with the numbers being kind of like that idea of anyway, basically the empty numbers to begin with, because again, we want our kids thinking about what's happening in the story rather than just doing something with the numbers. So if we have some horses playing in the pasture and some horses go into the barn to drink some water, and then that idea of being able to ask a question, what question do you think we're going to ask, you know? And so, okay, if we have 14 horses and 7 horses go to the barn, and then how many horses are still left playing in that pasture? These are all things that we want our kids to be able to do independently, so that they can become problem solvers. We have to be able to ask questions. We have to be able to think about what's happening in the scenario rather than just taking these numbers and saying, you know, if we just saw the 14 and 7, you already know that half of your class is going to add those together. Some of your classes, you know, have, I mean, a group of kids are going to add, a group of kids might subtract, a group of kids, you know, they're going to be doing, honestly, they're going to be doing whatever it is that you taught them to do the day before or that day, you know, kind of a thing. What were you working on? That's what they assume they're going to do. But we don't want them just doing stuff with the numbers. We want them making sense of what are these horses doing? And did horses leave or did more horses come? So is our number going to be bigger or is our number going to be smaller? And about, you know, kind of getting that estimation and talking to them. So if we're talking about the horses that are still left in the pasture, are there going to be more than 14? Are there going to be less than 14? And again, students were lined up to walk to lunch. There were boys and girls in line. So we're looking at a comparison problem, difference unknown. So there were 12 boys in line and 17 girls. And then that idea, how many more girls were there in line? And that we know for our young learners, these questions are difficult. How many more girls? Because it's such an abstract thing to think about when we're comparing. So what I might do, I can still ask this kind of question, but now I might say, how many more boys do we need so that there are the same number of boys and girls? This gives this idea that they can directly model this now. So it makes this problem, just by changing the question or by adding on to the question, it makes it a much more doable problem for our little ones. So again, especially if I was doing something like this in kindergarten, first grade, this is something that we do a lot of. And it can be really challenging, that idea of how many more girls, you know? But again, can I just change it for some of those kids that are struggling, you know, with, what do you mean, how many more girls? What does that even look like? What does that mean? How many more boys do I need so I have the same number of boys to girls? Oh, you know, I need 5 more boys so that there's the same amount of boys and girls. Oh, so that means there are 5 more girls in line than there are the boys. And we want to talk about that with our students. And then we want them to be able to model that with cubes, right? So they're understanding this idea of comparing, but then the idea of, oh, I need this many more so that they're both equal, so that they both have the same amount. Again, we have, you know, a lot of different ones. I wanted to go ahead and share that with you. Like I said, it is linked. Oops. It is linked in here in the slideshow. And then so CGI, I was trained in CGI, cognitive guided instruction. I started my math journey back in, so now I forget if it's 2012, 2014, somewhere in there. Anyway, I started my math journey, and I started with Extending Children's Mathematics. That was the book that I started with. I was teaching 5th and 6th grade at the time, and I literally worked my way through that book. I talk about, I was in a district that was encouraging us as teachers to understand mathematics, therefore, so that we could help our students understand, build more number sense. And so the district allowed us, those who wanted to, or those of us that were maybe voluntold to, you know, we got to work our way through these books. And I literally did just one or two problems a day from each of these pages. And I learned more about mathematics and number sense that year. I'm sure I learned more than the students did. But I also look back and I'm surprised with the amount of number sense that my students built that year. And so then I ended up I ended up becoming a math coach for the district. Then I decided to go into administration. Anyway, then I ended up moving out to Tennessee, and I taught third grade. And then I came back to California and I taught first grade. Some of the most fun experiences of my life was being able to use this knowledge from the CGI books and use the information and just play math with my students. So much fun. But I highly recommend them, recommend these books. The young children's mathematics, if you are teaching, kindergarten or younger children's mathematics, if you are teaching 5th grade and under, extending children's mathematics, that idea that really is hitting. I mean, again, all of these are for, I think, all teachers, but really the idea with the fractions and decimals, if you teach 3rd grade or above, I just think it's essential. And then thinking mathematically, and it's really tying that algebraic thinking, into it. So I highly recommend that. Another thing, Pam Harris, if you haven't listened to her podcast, I highly recommend it. So this is, which I'm running out of time here, but this is, if not subtraction algorithm, then what? I highly recommend listening to this. I've learned a lot, about mathematics as well by listening to some of these podcasts. So thank you guys very much for joining me today. I hope you have a wonderful rest of your June and have a nice summer.